This video is on analysing infrared spectroscopy. Infrared spectroscopy is one of the methods that chemists will use to determine the structure of a particular molecule. We use it to specifically determine what functional group is present in a molecule, and for your AS course you're going to focus exclusively on organic molecules and their infrared spectroscopy. You can do infrared spectroscopy with inorganic molecules, but we're not going to discuss that in any sense. So we need to understand why infrared spectroscopy works, how it works, and then we look at the spectra that we get produced, and it's really the analysis of that we need to focus on. So infrared spectroscopy works on the basis that when you shine radiation onto a chemical, it will absorb the radiation that corresponds to a wavelength between 1.5 and 15 micrometers, which is the infrared part of the electromagnetic spectrum. When that energy is absorbed, this causes a change in the vibrational energy in the bonds, and that happens at a very specific frequency. So all of the bonds will absorb energy, and this will cause one of two modes of vibration, either stretching or bending. So if you look at a carbon-hydrogen bond, that bond behaves very much like a spring, and if it absorbs more energy, it will oscillate at a higher frequency. It will absorb the energy that corresponds to that frequency of vibration. Equally, if we've got a carbon and two hydrogens, we could get a bending oscillation. So we end up with three modes of vibration: symmetrical stretching, asymmetrical stretching, and bending, which are represented like so. A molecule like hydrogen bromide only has one vibrational state because it can only undergo stretching, and because it's just only got two molecules in, there is no difference in symmetry. And the rule is, the weaker the bond, the less energy required to stretch it. So bonds vibrate on their own unique frequency, and the frequency that they absorb depends on the strength of the bond, the length of the bond, and the mass of each of the atoms involved in the bond. So most bonds will vibrate at a frequency between 300 and 4,000 centimeters to the -1, which we call a wave number, and that's the infrared part of the spectrum. We use it, like we said, to determine the functional groups present. Now, the wave speed equation tells us that the wavelength will multiplied by the frequency will be equal to the wave speed. Now, because we're talking about light, the wave speed is constant. Now, we don't use wavelength on our infrared spectra because if wavelength was to increase, then that means frequency would decrease. And the reason that we're not interested in that relationship is because frequency is related directly to energy, so energy is directly proportional to frequency, which we represent in chemistry with this V symbol, which looks like a V with a bit of a quiff. So energy is directly related to frequency, but because wavelength is inversely proportional to frequency, we want something that's directly proportional. So we use wave number. So wave number is 1 over the wavelength. So if, for example, I'd got a wavelength of 300 nanometers, then if I wanted to know what the wave number that would correspond to, I could do 1 divided by 300, and if it's nanometers, it would be times 10 to the -9, and that would give me an answer in wave numbers that would correspond. In this case, I would get an answer per meter. We're interested in per centimeter because it makes the numbers nice and easy. So the way an infrared spectrometer works is a beam of infrared radiation is passed through a sample. We have to pass it through a reference cell as well, and then we subtract those two samples in order to produce, so we've just got the chemical we're interested in. And we fire a full range of frequencies through. Now the molecules will absorb only some of those frequencies, and we analyse the transmittance against frequency. So which frequencies are transmitted, which ones pass through, and then the peaks then correspond to which ones are absorbed. And we measure that in wave numbers, and the units of which is centimetres to the -1. So as an example of an infrared spectra, we get a pattern that looks like this, and we get peaks that correspond to specific bond vibrations that then allow us to determine some of the key features of the structural group for a molecule. So for ethanol, for example, we can see there's the OH bond, and that's really the biggest characteristic vibration for an alcohol, the CH bond, at about 3,391 in this case. You also get always around about 3,000, you will get a vibration that corresponds to CH bond vibrations, and also we're going to get a CO vibration here. That's much further down the spectra, and we don't tend to focus on this region because this is the fingerprint region. So we use it for lots of different things. We use it to analyse paint fragments, we use it to identify the degree of unsaturation occurring in polymerization, we use it to ensure that the chemicals we produce are pure in drug analysis and in breath testing. So let's have a go at identifying some of the key peaks. So for example, this is an example of a key peak that is characteristic of the functional group that is present. Anything that is below approximately 1,500, this is the fingerprint region. So each of these vibrations, for example, we know that a vibration at about 3,000 corresponds to a CH vibration. Now, one of the peaks down here will also correspond to a CH vibration, but rather than being a CH stretch, it would be a CH bend. And we're not interested in trying to identify what each one of these peaks is. The only reason we use it is to basically clearly identify a chemical when we know what it is, so we can compare the fingerprint region. So we're interested just in values higher than that. So this has a key peak at just about 1,700. So that will correspond to a C double bond O, so a carbonyl group. Just to clarify the point about wave numbers, wave number is inversely proportional to wavelength, which is what we know from the equation we saw. So as the bond enthalpy increases, as the strength of the bond increases, the wave number increases. So as the wave number increases going this way, the bond enthalpy increases. So the bonds at this end have a higher bond enthalpy than the ones at the other end. So this is what you get from your data sheet. So the ones in blue are the ones that you mainly need to focus on. All organic molecules will have a peak at around about 3,000 that corresponds to a CH bond. Then if we focus on, if we've got just an alcohol, then we would get a broad peak at about 3,300. It covers, it's quite a broad peak, and that would correspond to an alcohol. You could have a carbonyl group, and that would correspond to a bond vibration of around about 1,700. If you had both of these, then you would get a carboxylic acid. So a carboxylic acid will have this vibration, and it will also have an OH vibration, but it will be slightly lower down because of the effect of adding this group on this bond. It will be further down, but it will be very broad. So let's have a look at some examples. In this one, we can ignore below the fingerprint region. We can see here at about 3,000 we've got our CH bond vibration, and we have a key peak at 3,230 to 3,500, so that is going to be an OH. Now we don't have enough information to definitively say what the alkane part of this is yet, but we will move on to that. So this one could be, well, this one is methanol. This one has a key peak that corresponds to 1680 to 1750. So from your data table, you should see that will correspond to a C double bond O. So this molecule is clearly an aldehyde or a ketone. We can't say which one at the moment, but we know it's one of those two. And we also have a bond vibration at 3000, so that just again confirms our CH bond. This is propanal. Now let's compare this to the carboxylic acid, propanoic acid. We would still expect to see this C double bond O, which we do in the same region here. We get the same C double bond O. And you can see how there is now a much broader peak over this region from 2500 to 2300, and that corresponds to our carboxylic acid. So you can see there is the CH vibration there as well, but this is definitive proof that we have a carboxylic acid, and so this is propanoic acid. Here's a couple of questions that we discussed in class. So first of all, an organic compound has an absorption peak at the infrared spectra of 1700 centimeters to the minus 1. There is no peak at a wave number greater than 3000. What functional group must be present? So it had to be a carbonyl group, a C double bond O, and that it had to be in an aldehyde or a ketone, because there's no bond vibration above 3000. So that means there's no OH hydroxyl group, so it can't be an alcohol or a carboxylic acid. State the approximate wave numbers for the key infrared absorptions for the following molecules. Well, pent-2-ol, it's just the alcohol, so we're going to get, in each of these three cases, we're all going to get a vibration that corresponds to 3000 because of the CH bond, so I'll just do that first. But the pentanol, we're going to get a peak that will be broad between 3200 and 3550 centimeters to the minus 1. In this case, we've got 2 hydroxy pentanal, so the al bit tells us it's an aldehyde, 2 hydroxyl, so we've got this bit is an OH group, so we're going to have the same bond vibration, but we're also going to have for this one a bond vibration that corresponds to 1640 to 1750 to the minus 1. And butanoic acid, we would get this same bond vibration again due to the O double bond O group, and we wouldn't get this vibration for the OH group in the butanoic acid. It would shift down slightly. We'd get a very, very broad peak between 2500 and 3300 centimeters to the minus 1. If you don't understand any of the things that we've done with infrared spectrometry, you need to make sure that you ask your teacher about it. Have a look carefully at the exam questions. As long as you can look and identify the peaks and use this to make a definitive statement that says simply this functional group is present, then that is going to provide a really powerful tool towards our chemical analysis.